Silicon carbide fourth generation chip technology shapes the future of industrial drives. Hello and welcome to ROHM session at Bodo's Wide Bandgap event. My name is Rony Karim, Application Marketing Manager at ROHM Semiconductor, and I will be with you for next 10 minutes to show our latest innovation in silicon carbide. Why do we need to implement silicon carbide in industrial drives? To understand this question, we must know the market trend of industrial drives. If we look at the market trend, we will see several facts. First, cost-saving approach. That means smaller heatsink, smaller passive component, zero maintenance means no fan requires, energy saving means less electricity bill. Secondly, space-saving approach. That means smaller size of inverter or drives, and some cases higher degree of integration, meaning built-in motor and drives. And finally, standard and regulation compliance, which is imposing lower losses, higher efficiency system, and less CO2 emission. By translating all these factors in semiconductor industry, we could realize that we need a semiconductor technology which will have higher power density, which will allow higher switching frequency, which will have higher junction temperature, and finally will generate lower losses at slow DVDT. And all these requirements could be fulfilled and only be fulfilled by implementing silicon carbide. We could see the standard topology of a low voltage drives connected to a three-phase mains. The rectifier block is responsible to convert AC voltage to DC voltage. The brake chopper will stabilize the voltage, and the power stage or the inverter will convert the DC voltage to AC voltage according to load requirement. Let's estimate the power losses using our silicon carbide fourth generation and compare the result with IGBT-based power module. To compare the losses, we have taken two different cases. Case 1 requires higher output current, which is 31 amps, and has also higher overload conditions. And we have considered 150 amp IGBT-based base placeless module. For case 2, we have considered 50 amp IGBT module considering low output current, which is 13 amps, and lower overload conditions. And we have compared the results with our 18 milliohm 1200 volt silicon carbide fourth generation device in TO247 package. In case 1, we have taken two 18 milliohm devices in parallel. And in case 2, we have considered single 18 milliohm silicon carbide fourth generation device. We have compared the power losses with IGBT modules. The losses of silicon carbide fourth generation are at least 50% lower than IGBT modules. Although the switching frequency has been increased to 16 kHz, silicon carbide fourth generation still provides significantly lower losses than IGBT modules. The junction temperature of silicon carbide fourth generation is also remarkably low. Silicon carbide fourth generation performs extremely good in inverter application, and it generates very low losses. By using fourth generation of our silicon carbide, we could either reduce the inverter size or we could increase the output power of the drives. We could replace IGBT modules with our discrete devices. Due to less heat dissipation, no fan required in the system means zero maintenance in the field. The heatsink shall be smaller in size or no need of heatsink. Finally, silicon carbide fourth generation will also allow to integrate the inverter and the motor in one housing. Brake chopper is used to burn the braking energy, which is not so wise considering energy utilization. So, the alternative and wise approach is to implement active front-end and penetrate back the braking energy to the grid. Let's implement our silicon carbide fourth generation device for active front-end application. 1200 volt, 40 ampere IGBT and 18 milliohm silicon carbide fourth generation in TO247 package have been taken for power loss calculation. The parameters for active front-end are also considered based on real application. Based on our simulation result, we could easily observe that the silicon carbide has at least 60% lower losses compared to the IGBT. Although the switching frequency of silicon carbide is 3 times higher compared to IGBT. Silicon carbide fourth generation increases the efficiency of active front-end. The total loss reduces significantly. So the system requires no fans, means zero maintenance, and the passive elements will be also smaller in size. That means it saves the space and the cost. We are achieving the best performance in drives due to our latest innovation in silicon carbide. You can see that our fourth generation silicon carbide has 40% lower on resistance compared to our third generation, and this fourth generation still has short circuit robustness. The benchmarking charts show that ROHM has the best trade-off ratio among the silicon carbide manufacturer in the industry. We are offering different on resistance value in 3 different packages in 1200 volt class as well as 750 volt class. We have developed an evaluation board in half-bridge configuration for testing the performance of silicon carbide fourth generation. The board is available and orderable from our website. We are completely vertically integrated company, which gives strong supply chain security for our customer. We are not only securing our supply chain, but also we are focusing on expanding our capacity to fulfill the market demand. We are the first semiconductor company who introduced silicon carbide commercially. We have long experience and expertise in silicon carbide technology. We are a vertically integrated company. We are aggressively investing to expand our capacity, and finally, we are your trusted and loyal partner.